today I'm going to present some of our recent work done jointly with Dr. Eric McLemore, who used to be at UF in AD, and now he's at Clemson University. And our co-advised doctoral student Han Yu Chan, who defended a couple of weeks ago. Well, almost defended, had defense. Now there is a need to finish the dissertation, and he will be on his way to the next job at as a postdoc at the University of Michigan. So I will focus on statistical modeling and uncertainty quantification for data produced by biosensors, which is the expertise of Eric McLemore's lab. And my expertise is statistics and applied machine learning. And we joined our areas of expertise and trained this doctoral student, Han Yu Chan. So let's start off with the talk is split roughly into two parts that are motivated by a single data set that was generated from experiments in the McLemore lab, which is what I will start off with. So the first part will be outline of the data and application of statistical machine learning methods to it. So the motivation here is that we would like to predict the level of bacterial contamination in water. And the original goal was to see how we can reuse water, say secondary types of water for instance, irrigation of lettuce. And the water may be contaminated by different bacterial cultures, such as E. coli, which is what was the focus in this motivating study. And so what we have is essentially a set of samples of water contaminated with E. coli. And I will spell out more details about that. And the goal is to use the measurements by biosensors to predict the level of contamination in a new sample. The level is unknown, say, taken in the field. So conventionally, this is done through the set of models called equivalent circuit model. And I will highlight what that is. So this boils down to taking the output of the biosensor, which is the so-called impedance curve, and then reducing it through this equivalent circuit model, or ECM, obtaining parameters that govern this particular circuit, and then fitting a nonlinear regression model to the concentration using these parameters. I will give very specific examples shortly. The problem is that it involves a lot of steps that may be unnecessary, and that was one of the motivations. So I wanted to see, can we bypass this step of building an equivalent circuit model, and instead just work with the raw data that are output by the biosensor. And that is the goal. Evaluate the suite of existing statistical machine learning algorithms, potentially see how those may be improved for this particular task. And there will be multiple subtasks that I will highlight shortly. What we have here is just the initial motivation. This is what the data look like. So in the top left, we have an example of this so-called impedance curves. On the so the fancy name is electrochemical impedance spectroscopy curves. What we have is the signal on the y-axis, and on the x-axis we have the frequency. And what we have on this plot is three impedance curves, one for a given concentration. So here the concentration is measured on the log 10 scale. So that is a 3 log CFU. This is a measure of abundance of the bacteria. I'm not an expert with the units, but that is how it's done traditionally. So this is the concentration. When I say concentration, it will be the log concentration. That's what the curves look like. And then we have real and imaginary impedance curves. So these curves in real life, they are continuous. However, the instrument gives those values at a discrete grid of frequencies. And one can think of each curve as a vector of length 73. So we have length 73 for real impedance and the same for the imaginary impedance. So that is what the data look like. One can think of this as vectors, or one can think of this as functions. So for this study, we will be thinking them as vectors of features. Now on the right, what we have is summaries derived by this equivalent circuit model. And this equivalent circuit model has two governing parameters, resistance and capacitance. And so what the way it happens, again, I'm arguing not at the physical or chemical level, I'm arguing on the level of the data. So the input is one of these curves, say this green curve over here. Then it is fed into some proprietary software, and this software fits a circuit model. And the circuit model is governed by these two parameters, capacitance and resistance. And then those two parameters are used for additional steps, which is calibration, that is deducing the concentration based on the values of these two parameters. So statistically, one can think of this as a dimension reduction step based on some physical theories. Well, one analogy to that would be to use, say, principal component analysis if one is a statistician, which is what I will discuss shortly. But for now, this is a conventional way of how one works with this data. And on the right, we have plots. So this the plots of these two parameters versus the concentration. And so in real life, one would be given a new curve for which the log concentration is unknown. And the goal is to guess or estimate or predict the log concentration for that new curve. And say if it's done traditionally, then one could use training data, build a model similar to this that I plotted here, and try to deduce the concentration based on this plot. Say if capacitance is I don't know, somewhere in say 2000, then one can take the horizontal slice of this plot, and that would be the range of values for concentration between 2 and 4. So that's how it's done traditionally. What we are trying to do here is to bypass the step of equivalent circuit model and see if we can use the raw data directly coupled with statistical machine learning. So now available data, I already told you what an observation is. And an observation here is this vector of length 73 times 2. So that is 73 is the length of a vector for each of this imaginary and real impedance curve vectors. So those are discretized. So we have one sample. To this sample, we apply a biosensor, and we get this vector of length 73 times 2. So now about the design, we have 8 concentrations. So again, as I said, on a log scale. So on a log, these are 0, 1, 2, up to 7. And then we have 15 biosensors, or 15 replications. So that is for each of these 15 biosensors, we take 8 measurements that correspond to this log concentration. So that is what the data look like. Now, in terms of the model, in terms of the response or outcome variable. So here we will be trying to predict the log concentration directly. So here, this will be our response or target variable. One can work with the original low concentration, so that is, in this case, one will have 8 different low concentrations, or one can work with this aggregated data set where the last 4 low concentrations are collapsed in a single category. So why is that? Well, we can see from this plot on the right that if concentration is of 4 or say greater than 4, it is hard to distinguish between those concentrations based either on capacitance or on resistance. In real life, that would mean really that the concentration of a pathogen is high, and that's like how high it is. It is a secondary concern. It is just high or very high. In terms of models and predictors, we do not want to reinvent the wheel. We want to see how statistical machine learning methods pair with conventional approaches. So, and conventional approaches, so that is nonlinear regression models based on this equivalent circuit model parameters. Once again, those parameters are resistant and capacitance. These coupled with a nonlinear regression model are used as the conventional or baseline approach. In this models, as I will show on the next couple of slides, one makes use of a parametric nonlinear regression function. So this and people have considered multiple types. The question is whether those choices are adequate or not, and we will see how this can be generalized if not modified. So in terms of predictors, so we have ECM derived predictors. Then one can work with this raw impedance curve data. So specifically this one that I have on the left, and potentially one can combine the two sets of parameters together. So that is, maybe these ECM models help us derive something that machine learning is not able to. And as far as predictive models go, the conventional approach uses nonlinear regression models with ECM parameters. This assumes that one knows the form of nonlinear regression functions. However, if this is not known, one would need to estimate the shape of this nonlinear regression function from the data. And this is where the second approach comes in. So this is generalized additive models with those same parameters. So that is just to see whether the choices of nonlinear regression functions used in the literature, whether those are sensible or not. And the last set of models is the statistical machine learning models, such as random forest, support vector machines, ridge regression, and so forth. So this is what conventional models look like. So yi is the response, which is the concentration or log concentration. Again, when I say concentration, I will always mean log concentration. Then this is related to the model parameters, to the equivalent circuit model parameters through this nonlinear regression function. And then we have the error term. So statistically, this is a nonlinear regression model. Now, what to use for this f? These are parametric functions, and this xi would be, say, one of these equivalent circuit model parameters. In the literature, people have used a modification of logistic distribution function. So if you look just on this expression in ratio, then what you will see is something like a logistic distribution function. This ratio takes on values between 0 and 1, and this transformation, what it does, it allows it to take values between C and D. Similarly, there is this so-called asymptotic function, which looks like a similar transformation, but applied to the distribution function of an exponential random variable. Again, we did not invent these choices. These are taken from the conventional literature. And here, the way it works is that there is this parameter theta. So theta here stands for a vector of unknown parameters that need to be estimated, which is this beta 0, beta, P, and D. So this would be estimated from the data. So the way it works is that if you know this parameter vector theta, then you know the whole function. That's why it's called parametric function. But what if we do not know what this nonlinear regression function f is? Well, then one would need to estimate it from the data. And one way in which this can be done is through this generalized additive models, or GAMS, which represents this function f as a linear combination of basis functions, say using cubic splines. And then the coefficients for the basis functions are estimated from the data. Of course, one needs to guard against overfitting, but this is a straightforward procedure. So typically, this is done by some type of cross-validation, or maybe k-fold cross-validation. So that is what these models look like. Yeah, and then for statistical machine learning models, what one would do is, instead of this f, which is given parametrically, one would replace it with a machine learning model. But conceptually, the idea is the same. Say maybe instead of this nonlinear regression function, one would use say a random forest or a support vector machine regression. Again, the actual names are not important. What's important is that one explores the diversity of those models, because a priori, we do not know which model is going to be the best. So now, working with this impedance curve models with the raw data, this is a high-dimensional predictor. Recall that the dimension is 73 by 2. So in data sparse situations such as the one that we have, recall that we have about 120 observations. One would need to do some kind of penalization of complexity, or variable selection, or data reduction. So one can do this automatically using techniques such as ridge regression or partial least squares, or one can first explicitly carry out the dimension reduction, and then work with the dimension reduced data. So here we use principal components analysis. Interestingly, the first two principal components explain more than 96% of variation in the data. And then equipped with these two principal components from the PCA, one can use multiple statistical machine learning methods without the fear of high dimensionality of our predictors. So, this is a list of methods that we have tried: support vector machines, support vector machine regression, random forest, and so forth. Here is another point. What if we wanted to combine the data? So that is there value in using ECM parameters coupled with the raw impedance curve data? This is another thing that we investigated. So conceptually this is depicted in this diagram. So one can use just the ECM derived parameters directly. I'm sorry. So on the left we have this ECM derived parameters. And then on the right, we have the parameters from the raw impedance curves. And one possibility is to just use these raw features and combine them with the two ECM parameters, and then feed statistical machine learning models. So here, one essentially puts all faith in the aptitude of this machine learning models. So let's just throw all the data at off-the-shelf machine learning models and hope that it does something meaningful. Another technique is one can think of this as feature engineering. So that is, what if we do not use this raw curves, but first try to extract information from them? So how can we do that? Oh, one possibility is to train machine learning models with this raw impedance data, and that is the branch that we in the diagram that we have on the right. And so each machine learning model produces a score. So this score can be used to predict the concentration. And then here, suppose we use the score as an intermediate variable. So that is, the score is combined with the ECM parameters. Suppose we use just one machine learning model, we have one score, and this is combined with two ECM parameters. So this gives us three parameters. And that is what one uses as inputs to new set of machine learning models for prediction. So this is what we have investigated, and in the end, these three parameters are combined using a generalized additive model to predict the final E. coli concentration. So when we do machine learning model, one really needs to guard against what statisticians call over-optimism or overfitting. Optimism is good, over-optimism is not good. So over-optimism means that our results on training data are much, much better than results on the test data. And ideally, what we would like is we want to have reasonably good results on both. To this end, one employs different types of validation and cross-validation throughout. So that is in calibrating tuning parameters of the algorithms, as well as when computing the test set performance. And here, because our individual observations are not really independent, one needs to do this in a very careful way. Why are the observations not independent? Well, because we have 120 observations, but only 15 biosensors. One would imagine that observations taken by the same biosensor would be correlated. Similarly, one can argue that maybe the solution of the bacterial concentration prepared by the same operator, so measurements taken on that would be correlated, as opposed to, say, one had different solutions prepared by different operators under different lab conditions. So these are really the things that one needs to guard against. And in this case, just randomly splitting the data set into training and test is a very, very bad idea in terms of assessing the real world operating characteristics of the algorithm. So that is, here, if it's done incorrectly, you will have great results on your training data set and on the test data set to the extent that those two will overlap heavily in terms of concentrations and biosensors. So here we are really trying to curb our over-optimism as much as possible, and we proceed with validation in the following setup. So we are trying two types of validation. The first is for the unseen biosensors. So that is, so here we have 15 biosensors, and suppose we use only 80% of those biosensors, so that is 12 out of 15, to train the model. And we test the models using the 3 biosensors that were not used in the training. So this is called for the unseen biosensor. Then we can do similarly for the unseen concentration. So that is, suppose we look at the known boundary concentration. So that is 1, 2, 3, up to 6. Then we leave out all the data for a single concentration. So that is 15 observations. So that goes into the test set. Say, suppose we take all the curves that correspond to log concentration equal to 1. So those all go to the test set, and they're not used in training. Then we use all remaining concentrations to train the model, and then we predict on this left out concentration. So each of this is done 100 times, by a random sample. What are some of the metrics? A common metric is the root mean squared error. What we're also doing is, and this is something that's not commonly done. Like, it is done much, much less frequently than using root mean squared errors. So that is, we would like to use a statistical test to see if one algorithm is superior to another one. So just the fact that the root mean squared error for one algorithm is lower than for the other does not imply that it is superior. So the question is, what should be a large enough difference for us to conclude that the difference is statistically significant? Well, here we took a statistical approach to this. Also, here, since we have 100 replications of this process, we can look at the uncertainty of our RMSE estimates. We can look at 95% confidence intervals. So let's take a look at some of the results and answer some of the questions that were raised. So first, let's use this data set with aggregated concentrations. Recall that here the original number of concentrations is 8, but in the aggregated data set, we are collapsing the largest 4 into a single category, and let's call this just 4. This helps models that are based on equivalent circuit model. Here, what we see is that out of these 3 models, the first 2 are nonlinear regression with logistic regression function and asymptotic regression function. And then we complement this with generalized additive model. We can see that the model with logistic regression function achieves the lowest RMSE, even though the results here are not statistically different. Still, this is good. It basically shows that these fancier methods were not able to improve over what's used in the literature. Now the question is it really what's used in the literature optimal, or is it really because we do not have much data? I lean towards the second approach, but this is not this basically one of the take-home messages is that what's used in literature is sensible given the typical amounts of data that appear in this study. Here, these are results of statistical machine learning model performance based on the root mean squared error when one uses the models based on impedance curves. So these are with and without explicit dimension reduction. And the different colors correspond to the aggregated data set, the one where the top 4 levels of low concentration are collapsed into a single one, and the non-aggregated, which is the darker shaded. And it's not surprising that the data set with non-aggregated concentrations, there one gets a worse result just by the design, because it is harder to accurately predict those high concentrations. What we have here is average root mean squared error values, as well as the corresponding confidence intervals for those. What we see is that some of the better statistical machine learning models significantly improve over the conventional approach, which is the nonlinear regression with logistic regression function. So the improvement is about 20%, and that is statistically significant. On the right, this is a complementary slide. What if one combines information from ECM derived parameters and statistical machine learning? Well, what we see is that there is a good amount of improvement when we use this intermediate score variable. This seems like an exciting result. However, I think this could be an artifact of how the data were collected. Specifically, in order for this to be used in real life, in my opinion, one would like to have a much finer grid of concentration for the training data. So that is here. What we had is a grid of 8 values. So low concentration 0, 1 up to 7. And we have 15 replications for each. In my opinion, it would be much better if we had a smaller number of replications, but a greater variety of log concentration values for the experimental data. Again, this is a subject for discussion. We did the best with the data that was presented to us. So far, this were the result for the first type of validation, which is for the unseen bias center. We also have results for the unseen concentration, and their results are considerably worse. So that is, it is harder in terms of the root mean squared error to predict the low concentration, for example, for which a similar concentration was not used in the training data set. It is interesting that some of the better models, such as ridge regression for unseen biosensor, were not competitive when we apply this to predict the unseen concentration. Again, the take-home message is that in order for making this more practical, one would like to have a greater range of low concentrations for the training data. Another bit of results is although secondary, is whether we need both curves, the real impedance and imaginary impedance. And based on our investigations, it appears that the impact of real impedance is negligible if we are already using imaginary impedance. And in some cases, say for non-aggregated concentration, it is interesting that if we use imaginary impedance, then say for SVM, the RMSE is 0.254. But if we add more data to it, so that is, if we add another curve, then the root mean squared error increases. It seems somewhat counterintuitive, but this is the artifact of the small sample sizes that we have. So that is, small sample sizes make it much harder to perform variable selection. So that is, in this case, for small sample sizes, for methods that supposedly should do automatic variable selection, well, it's not automatic as some people would like. So in this case, there is room for doing selection based on other principles. So this is as much as I wanted to say here. So we have some of the conclusions. So that is statistical machine learning models do help improve over the conventional approaches, and not only do they yield superior performance, which is not just in terms of reduced RMSEs, but also statistically lower root mean squared error values. It also allows us to bypass the need to first feed this equivalent circuit model to the data. So let me pause here and ask if there are any questions and how we are doing, because I could go for, say, another 10 or 15 minutes and outline the second part of the work, or we could stop here, call it a day. How do people feel?
I think we can go on. What do you think?
Okay, good. So then, as a motivating slide, let's take a look at this equation here. So in the first part of the presentation, we were fitting nonlinear regression models and statistical machine learning models to the response, which we designated to be the log concentration. Yeah. And looking at this model, one would ask, like, okay, so we have this mean function or the regression function, then we have the epsilon, which is the error. But then the question is, what kind of distribution should this epsilon have? Because it clearly cannot take, it clearly cannot have Gaussian or normal distribution. And why is that? Well, because in this data set, our yi's are just integers. So these are 0, 1, up to 7. And yes, this nonlinear regression function can take on a range of values, but still, this epsilon, if you ask, does this conform to the assumption of normality, the answer would be probably no. So then, why is this meaningful? Well, this is meaningful because in this case, there are nonlinear associations. Well, there are linear and nonlinear associations between the response and our covariance. And that is what drives machine learning. So some of those features are correlated, and we exploit these correlations when trying to predict the log concentration. So the motivation here is the following. Let's try to do things in terms of modeling how they really should be. And here we will model the individual impedance curves. So that is, impedance curve is the response, and it will depend on this concentration C, well as we have this W or omega, which is the grid of frequency values. So that is, we are swapping the order of our Y's and X's to what it should be. And then, so this allows us to account for different types of uncertainty from more fundamental statistical perspective. I will not go through all of those because that could lead to a discussion that is hours, if not days long. But what I want is just to highlight what are the steps here. So what we want is to build this so-called Bayesian calibration model so that we could quantify uncertainty about the concentration. So how does this work? Well, when we so how could this be done in a naive fashion? So suppose first that there are no unknown parameters in our statistical model, like everything is known except this concentration C0. And the way to think of this is the following. So nature chooses the value of C0, but this is not known to the statistician. Then nature runs the experiment with this biosensor, and this produces the vector of response values Y0. This is precisely this impedance curves that we have seen in the previous in the early slides of the first part. And then the goal is based on this observed value of the impedance curve. We want to deduce what this value of concentration C0 nature has chosen. And what we also want is to quantify uncertainty about this. So statistically, what we want is to get our hands on this posterior distribution of C0 given Y0. So from the practical standpoint, this will be done by Markov chain Monte Carlo. So we have the likelihood times the prior for C0, and then one would sample from this by Markov chain Monte Carlo or MCMC. The problem. So what is the problem here? The problem is that in order for us to evaluate the likelihood, so even in a simple case where this is some multivariate normal distribution, we would need to evaluate this function f at C0, and that is not allowed. So practically, what this would mean is for every proposed value in the MCMC algorithm, one would need to run to Eric's lab and ask them to do an experiment. The experiment would and even the experiment would not give us this value of f. It would give the value of the response or y that corresponds to this f. So that is the problem. So this f, it is regarded as known in the nonlinear regression framework, but in real life this is not known. So we need to somehow bypass the need for having this f. In addition, here what I haven't shown is that this is just a simplified picture. In real life, there are other parameters that are not known and they need to be integrated out. But I will, given the more applied focus on this presentation, I will ignore this. I'll just say that this is important to address. And so, how can one get get our hands on f? Well, we cannot. What we can do instead is to build an approximation to f. So in the literature about computer models, f is known as simulator, and approximation to f is known as emulator. And here we are trying to emulate f with this generalized additive model. I will not go into the details, but in a simple case, think of this as a way to interpolate or smooth the values of the observed impedance curves, and interpolation is done with respect to the different concentrations and different frequencies. And that allows us to build the approximation. and then we make use of this approximation in our model. I will not justify all the steps. I'll just give you the big picture. So this is stated for a model for data that come from a single bias sensor. So this is what the model looks like, and the big picture is that we have replaced the simulator F with the emulator F hat, and we will proceed with this model by Markov chain Monte Carlo sampling. So now, how can one generalize this to multiple to outputs from multiple bias sensors? Well, one would need to account for the variation incurred by different bias sensors on the same concentration, but this is done with the help of a random effect. I will not go into details, but this is doable, and surprisingly, in this data set, the form of random effect is very simple. I was very surprised myself, like how simple it turned out. In other studies that I was familiar with, it's not that simple, but here it is just the vertical offset for those curves. So again, here one could try this for the unseen sensor and the unseen concentration. So what are the outputs that we collect? So the samples are collected by Markov chain Monte Carlo. We run this for 10,000 iterations, which is conventional. Part of those are discarded as the so-called burn-in period. And then based on the collected data, we estimate the predicted, we estimate the concentration as the sample average, and we estimate we obtain the prediction interval for this low concentration. In Bayesian statistics, this is known as credible interval, using sample percentiles or sample quantiles. So that is once again here is what is going on. So this approach, Markov chain Monte Carlo, proceeds iteratively, and at each iteration we sample all of the parameters from their conditional distributions. And ultimately, we mainly care about this concentration C0, and that is what we collect. So in terms of the result, and here this is very much work in progress. However, I wanted to show you some of the optimistic results, but these are not final results. So for the unseen bias sensor, we have the root mean squared error, but okay, so what? This would be obtained. This could be obtained by a regular statistical machine learning method. Here we have the coverage rate for 95% prediction interval. This is interesting. Like, why do we care about this? Well, in these models, there is a lot of model misspecification that goes on. Many of those models are equipped with automatic formulas for confidence intervals for prediction intervals. However, they assume that model assumptions are satisfied. But in real life, model assumptions are very rarely satisfied. So the question is, what would be the real life coverage of an interval that you obtained using formulas that are, say, for 95% coverage? Well, it could be that the nominal coverage is 95%, but the real coverage is 60% or 70%, or sometimes it's 0%. Let's face it, we have been to situations like that. And so what we have is that the coverage for the unseen sensor is very close to nominal. This is very reassuring. So this is for the unseen sensor. However, for the unseen concentration, the coverage is lower than nominal, and this is what we are trying to address now. This is an example of what may be going on. So that is if we go with a 95% interval from our approach, then this would be over optimistic because the real coverage is only 83%, and we want to guard against that. We investigated how many replications we need, but let's keep this. This is interesting, like how this compares with other approaches. And the take-home message is that we have a nominal coverage rate. We have an empirical coverage rate, which is better than for the competitive methods, and we have the width. This is the width of the prediction interval that is lower than the competing method. So that is these two figures, the width of the interval and the coverage rate, are most important pieces that come out of this Bayesian framework. So this is really what where I would like to focus here, so that we have about 10 minutes for a discussion. What we have done is we have incorporated more sensible assumptions about the byte-sensor output, and even though the approach is more computationally intensive than conventional approaches, this really pays off because we are getting more accurate prediction result. So with the primary emphasis on prediction interval. So acknowledgements. This is work that was done jointly with Eric McLemore and with our jointly advised student Han Yu Chan, who had his defense in AB a couple of weeks ago and is heading as a postdoc to the University of Michigan later this summer. Thank you very much for your attention. We have about 10 minutes for questions.
Do we have any question from audience? I have one question.
Yes, absolutely. Yeah.
So you said for the second projects that you mentioned, the unseen concentration has a lower accuracy. Does that mean we need to have certain concentration only to work for this model? What does that mean? I couldn't really understand what.
Okay, okay, good. The setup is exactly the same as in the first part. So that is the question is, how do we validate how well the model works? And yes, so here this is the motivating slide. So for the unseen concentration, we allocate all the data for one concentration to the test set. So that is so suppose we take a low concentration 1 and it's not used in training, it's only used for testing. What we are seeing is that so far our method does not perform as well as if this concentration were in the training data set.
I see. So does that...
So basically the take-home message is that we are working with the data that we have been dealt, and our recommendation would be, instead of having 15 replications for each concentration, we would rather have much smaller numbers of replications, but for a greater number of unique concentrations.
I see.
So essentially, like how can we make up for the unseen concentration? Well, we do some kind of an interpolation, right? So if, say, the low concentration for 1 was missing, then maybe we could take the response for low concentration 0 and low concentration 2 and somehow connect the dots or smooth that. However, the bigger the gap, the lower is the accuracy of the approximation, and that's what seems to be happening here.
I see. But so for that case, if you have separate model for different concentrations, that probably help to improve accuracy?
No, because because in real life you do not know what will be the concentration that you are trying to predict. And if you know the concentration that you are trying to predict, then you don't need any statistics. You just go with it.
Yeah, that's true.
So here what we're trying to do is to borrow information from seen concentration to say something new about the unseen concentration.
Okay, yeah.
And the coarser the grid of the seen concentration, the harder it is to say something that's not completely wrong about the unseen concentration that's in between.
Okay.
So in some sense, this is related to the problem of approximating a function based on the limited number of functional evaluations. So that is, you have a function, say f of x, and x is between 0 and 1, and you want to recover this function on the interval from 0 to 1. And ideally, you want well, what one can do is take multiple evaluations and then do interpolation or smoothen. So one would do interpolation if the function is observed without error, and smoothen is if what we observe is a function plus the error, like we have here. And really, from the standpoint of mathematics, the bigger are the gaps in the data that you observe, the harder it is to recover the function.
Right. Yeah.
So in that sense, we would, even though the data are noisy, to compensate for the noise, we would like to have some number of replications. But here there is a trade-off between how many replications per concentration one can take and how many different concentrations to explore. And our current message is that reduce the number of replications from 15 to a smaller value, but instead sample a greater number of unique log concentrations.
I see. Any other question from audience? Okay. If not, I'd like to conclude the seminar series. Let's give a big hand to Dr. Nikolai Bliznyuk. Thank you again for attending the seminar series. Our next seminar will be in the fall semester. I'll see you in the fall. Thank you.
Thanks, everyone. Thanks, Dana, for organizing this in view of the contingencies that we have experienced today.